Hello everyone, in this video, I'm going to show to you how to derive the mean, the variance, and the moment-generating function for the beta distribution. Beta distribution is a continuous probability distribution with a probability density function or PDF shown in here. Now the function in here is a beta function. It is defined to be this one. Now let us derive the mean. Mean is equal to expectation of x. And since this is a continuous probability distribution, it is equal to the integral of x times the probability density function, which is this one in here, then dx. This x is from 0 to 1, so we have here 0 to 1. Then this beta function, which is this one, is a constant, so we can move this one outside of this integral, so we have this one from here. Then let us combine both x, this one and this one, so we have here x raised to alpha minus 1 plus 1 is alpha, so we have here x raised to alpha. Then the rest of the terms, this in here. Now if we compare this integral expression with this integral expression, they're almost the same except that this is alpha minus 1 while this one is alpha. So if we let this alpha to be alpha plus 1, then we get here alpha plus 1 minus 1, which is alpha. Then it will make this expression to be same with this one. So let this alpha to be alpha plus 1. So we have here big beta of alpha plus 1 beta is equal to integral of x raised to, when we substitute this alpha by alpha plus 1, we get here alpha. Then the rest of the terms, this in here. Then this one now is same with this one. Then our mean is equal to this one, which is big beta of alpha plus 1 beta in here. Then over big beta of alpha beta, which is this one. Now to simplify this one, we need to transform this into in terms of gamma function. We can do that using the identity, which is a relationship between beta function and gamma function. So if this identity is unclear to you or you don't know about this identity, I have a video that shows how to prove this one. So I provided the link in the description below so you can check it out. Now this one is same with this one, big beta of alpha beta, but how about for this one? If again we replace this alpha by alpha plus 1, we'll get big beta of alpha plus 1 in here, but also we need to replace this alpha in here and also this alpha in here by alpha plus 1. So we have here big gamma of alpha plus 1 from here, and also in here we have big gamma of alpha plus beta plus 1 from here. Then substituting this in here, we'll get for this one big beta of alpha plus 1 beta, which is same with this one, we have this one from here. Then times for this one, which is same with this one, we need to multiply this one by the reciprocal of this one, since this one is at the denominator. So we have here big gamma of alpha plus beta, which is from here, then over big gamma of alpha times big gamma of beta, which is from here. Then we can cancel out this big gamma of beta and big gamma of beta, and then let us rearrange this one. So we have here big gamma of alpha plus 1 over big gamma of alpha in here, times big gamma of alpha plus beta over big gamma of alpha plus beta plus 1 in here. Then this one again can be simplified using another identity, which is a recursive identity for a gamma function. This one, big gamma of alpha plus 1 is equal to alpha times big gamma of alpha. Then again, I have provided the link in the description below for the proof of this identity, if this one is unclear to you or you don't know about this identity. Then from here, big gamma of alpha plus 1 over big gamma of alpha is equal to alpha. So this one is same with this one, so we have this one alpha in here. But how about for this one? If we replace this one alpha in here by alpha plus beta, we get big gamma of alpha plus beta plus 1 in here. Then we need also to replace this alpha in here and alpha in here by alpha plus beta. So we get here big gamma of alpha plus beta from here and alpha plus beta from here. Then this one is the reciprocal of this one, so it is equal to the reciprocal of this alpha plus beta. So we have now our mean, which is this one, equal to this one, which is alpha in here, times this one, which is the reciprocal of this alpha plus beta, which is this one, 1 over alpha plus beta. Then we have alpha over alpha plus beta, which is this one. So we have now this one for our mean for the beta distribution. Now let us proceed with the derivation of variance. Variance has the formula expectation of square of x minus expectation of x. we have another formula for variance, which is expectation of x squared minus square of expectation of x. This formula here is derivable from here. For the expectation of x, this is same with the mean, so we have derived it to be alpha over alpha plus beta. So we can use this one in place of expectation of x. Now for the expectation of x squared, we haven't derived it yet, so we need to derive this one first before we can derive our variance. For this derivation of expectation of x squared, the approach in here will be similar to the approach that we have done in our derivation of mean, which is expectation of x. So if you didn't skip our derivation of mean, then the approach in here for the derivation of expectation of x squared will be somewhat familiar to you. Now since this one, beta distribution, is a continuous probability distribution, it is equal to the integral of x squared, which is from here, times the probability density function, which is this one in here. Then this beta function, which is this one, is a constant. Then we can move this one 1 over big beta of alpha beta outside of this integral, so we have this one from here. Then let us combine these x's in here. So we have here x raised to alpha minus 1 plus 2 is alpha plus 1. So we have here x raised to alpha plus 1. Then the rest of the terms, these in here. Now, if we compare this integral expression with this beta function, they are almost the same except that this one is alpha minus 1 while this one is alpha plus 1. If we replace this alpha by alpha plus 2, then we have here alpha plus 2 minus 1, which is alpha plus 1, and it will make this integral expression to be same with this one. So now let us replace this alpha by alpha plus 2, which is this one, big beta of alpha plus 2 beta. Then it is equal to x raised to alpha plus 2 minus 1 is alpha plus 1, which is this one. So now this one is same with this one. Then we can replace this one by this one, big beta of alpha plus 2 beta. Then our expectation of x squared is equal to big beta of alpha plus 2 beta, then over big beta of alpha beta in here. Then similar to what we have done in our derivation of mean, we can simplify this one by transforming it into in terms of gamma function, using this identity, which is a relationship between beta function and gamma function. Now this one, big beta of alpha beta, is equal to this one. So we can use this one in place of this one. But how about for this one? So we can have this one by replacing this alpha by alpha plus 2. So we have here big beta of alpha plus 2 beta is equal to, replacing also this alpha in here and alpha in here by alpha plus 2, we have big gamma of alpha plus 2 from here and big gamma of alpha plus beta plus 2 from here. Then substituting this in here, for the numerator, which is same with this one, we have this one in here. Then times, for this one, which is big beta of alpha beta, same with this one, we need to multiply the reciprocal of this one with this one, since this one, big beta of alpha beta, is at the denominator. So we have this one from here. Then we can cancel out this big gamma of beta, and also in here, big gamma of beta. Then we can rearrange this expression into big gamma of alpha plus 2 in here over big gamma of alpha in here, then times big gamma of alpha plus beta in here, and over big gamma of alpha plus beta plus 2 in here. Then similar to what we have done in our derivation of mean, we can simplify this one using another identity, which is a recursive identity for gamma function. So we have this one, big gamma of alpha plus 1 is equal to alpha times big gamma of alpha. Now, if we replace this alpha by alpha plus 1, we'll have big gamma of alpha plus 1 is alpha plus 2. And also by doing that, we need to replace also this alpha in here and alpha in here by alpha plus 1. So we have here alpha plus 1 from here and also alpha plus 1 from here. Then this big gamma of alpha plus 1 is same with this one. So we can replace this one by this one, alpha times big gamma of alpha, resulting in here. Then if we divide this big gamma of alpha plus 2 by this big gamma of alpha, so we have this one, alpha plus 1 times alpha for this one. Then this one is same with this one, which we can replace it by alpha plus 1 times alpha. But how about for this one? Let us replace this alpha by alpha plus beta. So we have here big gamma of alpha plus beta plus 2 from here after replacing this alpha by alpha plus beta. Then by doing that, we need also to replace this alpha in here and alpha in here, by alpha plus beta. So we have here big gamma of alpha plus beta from here. We have here alpha plus beta plus 1 from here. And alpha plus beta from here. Then notice that this one is a reciprocal of this one. So this one can be replaced by the reciprocal of this one. So we have here, this one is same with this one, so we have alpha plus 1 times alpha in here, times this one which is reciprocal of this one. So we have here 1 over alpha plus beta plus 1 times alpha plus beta. Then simplifying, we have this one in here and this denominator in here. So now we have derived our expectation of x squared. Now for our variance, which is this one, expectation of x squared minus square of expectation of x, we can rewrite that in here. Then for expectation of x squared, we can use this one because it is equal to this one, expectation of x squared. So we have this one from here, then minus square of expectation of x. Expectation of x is our mean, alpha over alpha plus beta. So we have this one, alpha over alpha plus beta, as our mean that we have derived already. Then by algebra, we can have a common denominator for these two terms, which is alpha plus beta plus 1 times alpha plus beta squared. Now dividing this one, our common denominator with the denominator in here, we'll get alpha plus beta. Then alpha plus beta times this numerator, we have alpha plus 1 times alpha, which is from here, the numerator, then times alpha plus beta. Then we have minus, dividing this one, our common denominator, with this alpha plus beta squared, we'll get alpha plus beta plus 1. And then multiplying it by this alpha raised to 2, we'll get alpha squared from here, times alpha plus beta plus 1. Now we can multiply this alpha plus 1 by this alpha plus beta. So multiplying this alpha with this alpha plus 1, we get alpha squared plus alpha. Then plus multiplying this beta with this alpha plus 1, we get alpha beta plus beta. Then we still have this alpha in here. Distributing this negative alpha squared for each term in here, we'll get minus alpha raised to 3 from here, minus alpha squared beta, then minus alpha squared. Now, distributing this alpha for each term in here, we'll get alpha raised to 3 from here, plus alpha squared from here. Then also we have alpha squared beta from here, then alpha beta from here. Now we can cancel out this alpha raised to 3 and minus alpha raised to 3, this alpha squared beta and this minus alpha squared beta, this alpha squared and minus alpha squared. So we're left with alpha beta in here over this common denominator in here. So now we have our variance for the beta distribution, which is this one. Now let us proceed with the derivation of the moment generating function. Moment generating function has the formula expectation of e raised to tx. Since this beta function is a continuous probability distribution, it is equal to the integral of e raised to tx times the probability density function, which is this one in here, then dx. This x is from 0 to 1, so we have here 0 to 1. Now this beta function, which is big beta of alpha beta, is equal to this one, which is a constant. Then we can move this one over this beta function outside of this integral. So we have this one from here. Now for this e raised to tx, we can expand this one using the Taylor series for exponentials. So for this one, e raised to tx is equal to summation of tx raised to, let us use the variable k, then over k factorial. Then this is from k is equal to 0 until infinity. Then putting this one in here, we'll have this one. Now inside this summation, k here is treated as a variable, while this x is treated as a constant. So these remaining terms, x raised to alpha minus 1 times 1 minus x raised to beta minus 1, are treated as a constant. So we can move this inside this summation. Then we have here dx from here. Then, from calculus, we know that the integral of the sum of functions is equal to the sum of integral of each function. Then, for integral of summation of functions, using this concept, it is equal to summation of the integral of each individual function. So in here, we can interchange the integral sign and the summation sign. Then applying this one in here, we can interchange this integral and this summation. So we have this one. We have here summation of integral of this. Now in here, in this integral, t and k here are treated as constants. So we can move them outside of this integral. So we have this one from here, t raised to k, which is this one, and then over k factorial, which is this one. Then we can combine the x in here and x in here to have x raised to alpha plus k minus 1, which is this one. Now this integral expression here, integral of x raised to alpha plus k minus 1 times 1 minus x raised to beta minus 1 dx from 0 to 1, is somewhat similar to our beta function, which is this one. So let us rewrite this one below, which is this one. Now if we make this alpha to be alpha plus k, which is this one, then they are now the same. But also we need to replace this alpha by alpha plus k also. So this one, this integral expression is big beta of alpha plus k beta. So we can put like this instead of this integral expression. Now for this big beta of alpha beta, which is this one, is a constant for this summation, so we can move this one inside of this summation. Then we have now this one. Now similar to what we have done in our derivation of mean and variance, we can simplify this expression, this big beta of alpha plus k beta over big beta of alpha beta, by transforming it into in terms of gamma function, using this identity, which is a relationship between beta function and gamma function. So for the big beta of alpha beta, this is the same with this one. But for this big beta of alpha plus k beta, we can generate this one from here by replacing this alpha by alpha plus k. So we have here big beta of alpha plus k beta by replacing this alpha by alpha plus k. But doing that, we need also to replace this alpha in here and alpha in here by alpha plus k. So we have here big gamma of alpha plus k from here, and also in here we have big gamma of alpha plus beta plus k from here. Then this one, big beta of alpha plus k beta over big beta of alpha beta, which is rewritten in here, is equal to, for this one big beta of alpha plus k beta, which is same with this one, we can use this one in here. Then times, for this one big beta of alpha beta, which is same with this one, we need to multiply this one by the reciprocal of this one, since this one is at the denominator. Then now we have big gamma of alpha plus beta from here, and then over big gamma of alpha times big gamma of beta from here. Then we can cancel out big gamma of beta in here, and also big gamma of beta in here. Now we can rearrange this expression. In here we have big gamma of alpha plus k from here, over big gamma of alpha from here. Then times big gamma of alpha plus beta from here, then over big gamma of alpha plus beta plus k from here. Now similar to what we have done in our derivation of mean and variance, we can further simplify it using another identity, which is a recursive identity for gamma function. So which is this one, big gamma of alpha plus 1 is equal to alpha times big gamma of alpha. Now if we replace this alpha by alpha plus 1, we get big gamma of alpha plus 2. But doing that, we need also to replace this alpha in here and alpha in here by alpha plus 1. So we have this one, alpha plus 1 from here, and another alpha plus 1 from here. Now observe that this big gamma of alpha plus 1 is same with this one. So we can replace this one by this one, alpha times big gamma of alpha. Now if we replace this alpha again by alpha plus 1, then we have here big gamma of alpha plus 1 plus 2 is alpha plus 3. But doing that, we need to replace also this alpha in here and alpha in here by alpha plus 1. So we have here alpha plus 1 is alpha plus 2, and also same with here, alpha plus 1 is alpha plus 2. Observe that this one is same with this one, so we can replace this one by this one. So we have here alpha plus 2 from here, then this alpha plus 1 times alpha times big gamma of alpha, which is from here. Now we can continue the series. For a certain k, which is greater than or equal to 1, we have this one if you try to observe this pattern. For example, in here, big gamma of alpha plus 3, we have here big gamma of alpha times alpha plus 1 until we have alpha plus 3 minus 1, which is alpha plus 2. And also in here, we have here big gamma of alpha times alpha until alpha plus 2 minus 1, which is alpha plus 1. So in here, we have big gamma of alpha times alpha plus 1 until we have alpha plus k minus 1, which is this one. Now this k is greater than or equal to 1 because if this k is at 0 or below that, we will have here big gamma of alpha is equal to big gamma of alpha times alpha plus 1 until we have alpha minus 1, which we cannot attain since this alpha is greater than this one. But supposedly it should be increasing. So this equation is not applicable when k is equal to 0 or below. So we need to maintain this condition, k is greater than or equal to 1. Now, from here, big gamma of alpha plus k over this one, big gamma of alpha, is equal to this one, alpha times alpha plus 1 until alpha plus k minus 1. And we have a beta notation for this series, which is product of alpha plus r, in which r starts from 0, which is when this r is 0 we have alpha only, which is this one, until r is equal to k minus 1, which is this one, alpha plus k minus 1. Then this one, which is this one, can be used to replace this one, which is same with this one. Then how about for this one? Now if we replace this alpha by alpha plus beta, which is this one, we have big gamma of alpha plus beta plus k. From here, we need also to replace this alpha in here and alpha in here by alpha plus beta. So we have here big gamma of alpha plus beta from here. And we have here alpha plus beta plus r. From here alpha plus r when we replace this alpha by alpha plus beta. So we have now for this one, which is the reciprocal of this one. Then we can use the reciprocal of this one in place of this one. So we have here, for this big beta of alpha plus k beta over big beta of alpha beta, in here, is equal to this one, which is same with this one, in here, and then this one, which is a reciprocal of this one. Then we have this one from here. Then observe that they have the same limits, so we can combine them together as product of alpha plus r from here over alpha plus beta plus r from here, from r is equal to 0 until k minus 1, which is same with this and this. Now for our moment generating function, which is this one, let us rewrite this one below, which is this. We cannot easily replace this one by this one even though it is same with this one, because in here it starts from k is equal to 0. But our equation, in which we use for the generation of this one, is limited only for k is greater than or equal to 1. So what we're gonna do in here is to evaluate this one first at k is equal to 0, then add the summation of this expression from k is equal to 1 until infinity. So we have here, when k is equal to 0, t raised to 0 is 1. We have here 0 factor is 1, so 1 over 1 is 1. Then we have here, if k is equal to 0, so we have here big beta of alpha beta. Then it is same with this one, so this one over this one is just 1. Then we have 1 times 1 is 1, so we have here 1 when we evaluate this one at k is equal to 0. Then plus summation of this one at k is equal to 1 until infinity. Then we can use now this one in place of this one in here. So we have here this one, which is from this one in place of this one. Then now we have our moment generating function for the beta distribution, which is this expression.